Let's take a look on how to use integration to find the fluid forces on a submerged object in a fluid. As you can see here, we have some guiding formulas that we need to know from physics. That pressure is the force divided by area, which means the force is the pressure times the area. So if we imagined a submerged item, we have a certain amount of pressure on it, and the item it takes up a certain amount of area. So how can we write this force? So the force is going to be the pressure, but as you can see, the pressure depends on the weight density of the fluid. So for water, that happens to be 62.4 times the depth, right? Times the depth in the fluid, right? And then times the area that it takes up. And so that's kind of the guiding equation, and that's how we can remember what the integral is. So if we were to integrate with respect to the depth, we could write an integral kind of like this, right? A to B, that's just the depth. And I'm going to use y, so we're kind of imagining that we have a vertical axis here from A to B of our weight density times the depth function times the area, which we'll call L of y dy. Okay, and so that is, in a sense, the integral that we're going to use for fluid forces. So let's take a look at an example. So here we are asked to find the fluid force exerted on a given plate submerged in the water with a weight density 62.4. Okay, so what we want to do is use our formula, and we have everything we need. We can find a function for the depth. Okay, we'll set up a y-axis. Now this is a choice, and I'm just going to do, the numbers aren't really nice when you do this, but I'm going to set sea level at 0. Okay, we could describe the depth many other ways, but that way we're thinking of the water level at 0, just for this particular strategy. Okay, and so we can imagine what the depth is. The depth at any point in the water then is negative y. If y is negative 2, then the depth is 2. Okay, so that's our depth function. Our depth of y is negative y. And then we have the weight density, and then we just need the length. And so that is, we need to have an expression in terms of y of the length of our object at that depth. Okay, and if we go down here in the blue, and what we see immediately is that we're going to have two different expressions, because the length suddenly changes when we reach that level of the depth. So we want to be able to do is figure out an expression for the length, for the top, and then the bottom. Okay, so let's imagine this top part of this diamond. So we'll call this the top, and I'll just use x for a second, and we'll just say that we've made it x feet down. Okay, well, that means this is x and this is x, so the total length here would be 2x, and we know this would be x times root 2 over here. Now let's try to imagine the depth in terms of y. So what we want to do is just add the bit of the surface on top here. Okay, so we have the water, and this is 1 foot. Okay, so how deep is this? So we have x plus 1 is the depth. So the depth here is equal to x plus 1. But that's equal to negative y, right? So if we imagine that this is, right, this is negative y because we've gone down, equals to negative y. So that means that in our triangle, at least, x is equal to negative y minus 1. Okay, so now we can talk about the total length then. The length at any particular value of y is going to be negative y minus 1. Okay, That's great. And that's just check. When y is -1, we see the length is 0. That's right. When y is equal to, okay, we have to go all the way until the side length here is 2 feet. And we know if this is 2 feet, that this must be square root of 2, and this must be square root of 2. So we're going all the way until x is equal to the square root of 2. Okay, so if we go all the way until this is equal to the square root of 2, that happens when y is equal to negative square root of 2 minus 1. So that's the y value when we've reached this halfway point, negative square root of 2 minus 1. Okay, now, so that's going to help us describe the length. So now we just need to do the bottom, okay? So for the bottom, it's kind of similar. So by the way, the plate starts here when y is -1. So this is the top of the plate. Y is equal to -1, and then it goes down until y is equal to negative root 2 minus 1. Now what about the bottom? So the bottom, we just want to do the inverse. And so that's another square root of 2. So the length here, the length of y, we want it to start at negative root 2 minus 2 and then go down to 0. And it's at the bottom, y is at the bottom when it was at negative root 2. So we have another negative root 2. So negative 2 root 2 minus 1. So it went down root 2 here. And that's going to go down root 2 again. So that total distance on the bottom part is root 2 again. So the total distance from the whole thing is 2 root 2. So that's why the depth is 1 plus 2 root 2. And y is the negative of that. Okay, so a lot of things going on here, but this is the correct expression for the length of y, for when y is at the bottom. So what about the length of y? Well, we want the length to be the total length minus, right, minus what we had before, minus y minus 1. And if we take this, we get 2 root 2 plus y plus 1, and let's just check to see if this works. If y is equal to negative root 2 minus 1, we should get a total length of 2 root 2. Let's see. So if y is equal to negative root 2 minus 1, if we plug that in here, it subtracts 1 of the root 2, subtracts the 1, then the length of y is equal to root 2. Okay, that's good. So we actually need 2 of those, because that's just half of the triangle. Okay. Now let's just check if y is equal to all the way at the bottom. If y is all the way at the bottom, negative 2 root 2 minus 1. In that case, we get the length of y is equal to 0. Okay, so our function works, but the length as we've described it, is half the amount that we wanted to. So far, when I've set up the length, so far this is root 2, right? But we want the length to go all the way across, square root 2. Okay, so our length function for our integral, so now that we have an expression for the depth, we have an expression for the length function for the integral is actually going to be 2 times this. Okay, so I'm going to need to adjust that in the integral. So this length is just the length of half of it. Okay, so now let's write down the integral. So the integral equals to, this is the top integral, and we're going to go from -1, or we're going to go from negative root 2 minus 1 to -1. Okay, and then we have our 62.4, which is the density of water. Okay, and then our depth And then our depth right now is going to be negative y, right? Because that's how far it is down. Okay, and then our length. And the length of the first one is negative y minus 1. So we're going to have 2 times negative y minus 1 dy. Okay. And we're going to have the second integral plus the second integral. And we're going to go from all the way at the bottom. So that's negative 2 root 2 minus 1 all the way up to negative root 2 minus 1. And again, we have 62.4. The depth stays the same. It's at minus y. And in this time, our function, we're going to have 2 of the length. And our length is going to be 2 root 2 plus y plus 1 dy. And those are 2 polynomial functions that we can integrate, probably with the help of technology. But they're easy antiderivatives to find. Okay, and so at the end of the day, the setup is everything for these types of problems. This one was a little bit tricky. It probably would have been nice to maybe put y equals to 0 at a different position in the model, but it's pretty normal to put y equals to 0 at sea level.